Here comes 11.9. It's the last section for exam 3 on sequences and series. So, what are we going to do here? We are going to take what we began in 11.8 on power series and go to the next level. So, representing functions by power series. In 11.8, we learned what power series were. If you recall that first example, that introductory example to power series from the last time, we took a lot of time and we found a power series to represent e to the x. So you might remember that. Um, Turns out lots of other functions obviously have power series representations, and that's what we're exploring here in 11.9. We're going to go even further with that idea in 11.10 and 11.11, but that is for another test. Okay, so what's going on here? A big friend of ours is going to be the geometric series. We're also going to rely on the ratio test in one or two examples, I forget, but our big friend here is the geometric series. So remember that the series from n equals 0 to infinity, a r to the n, all those infinitely many terms will add up to a over 1 minus r, so long as the absolute value of r is less than 1. Okay, so what's the idea here? You notice the sun's kind of coming out here. So we're getting a shadow from the cord of my camera. Hopefully that's not too distracting. It wasn't there a moment ago. The sun came out from behind a cloud. Okay, anyway, let's go for it. Our examples are going to say represent by a power series and then find the interval of convergence. Okay, so part A doesn't get any more straightforward than this. Let me go ahead and bring that geo series back on the screen. How about something like f of x equals 3 over 1 minus x? Okay, so why is geometric series so helpful? That function looks very much like what the infinitely many terms in a geoseries add up to, right? So we can see the a, we can see the r is x. Well, if these are equal, then we can just rewrite our f of x like this. The summation from n equals 0 to infinity, 3x to the n. There's our a, there's the ratio, the common ratio you call it. R equals x here, boom, we got it. Now, if we were in class, what I would do is jump onto Desmos, and it's really interesting to graph this original function and graph maybe several terms of this summation, maybe like 3 or 4 or 5 terms, and you'll see how this summation, the graph of that, will very closely resemble the original f of x, but only around where this thing converges. So let's look at that further, and that's the second part. What's the interval of convergence? Well, it's where the absolute value of x is less than 1. Here r is less than 1. Here r is simply replaced with x. Oh, yeah, I've got that note. Compare the graphs. But for the interval, all right, there it is, way down on my page. We're going to take the absolute value of x is less than 1, right? Because that's when it would converge. So that's when x is between -1 and +1. The interval of convergence is right there from -1 to 1, not including the endpoints themselves. Okay. Now here we know that we will not include the endpoints themselves because for a geometric series, that value has to be strictly less than 1. So if we got to -1 or 1, we know that that would equal that wouldn't converge anymore. So here we actually don't have to test the endpoints. We know it, that those endpoints are going to diverge. Okay, so let me pause here, give you guys a chance. Go into Desmos, graph this, and maybe graph, I've got the first 4 terms. 3 plus 3x plus 3x squared plus 3x to the third for our series. Take a look at that graph. You can notice it's been centered at 0, if you remember the form for power series. And think about its interval of convergence. When it gets close to 1 and when it gets close to -1, those two are not going to be a good match anymore. It's going to diverge. But within -1 to 1, the more terms you get, especially, the more closely that series resembles the original function. Really, really cool. So why is this? Kind of hints at, what's the significance here? Why do we have these things called power series? A big motivation for it in this day and age, of course, is technology. So it's much easier for a calculator or a computer to think about a polynomial like this power series would give. It's super awkward for a software program to recognize 3 divided by 1 minus x. That's filled with all kinds of problems, and I'm not an expert in that area, but I'll just say computers are designed to interpret polynomials, not rational expressions. Why is that? Well, we can kind of get a clue as to like, well, derivatives are super easy for polynomials. Integrals super easy. It's so easy to evaluate a number for a polynomial versus something like this. When you grab your calculator, scientific calculator, graphing calculator, computer system, it doesn't actually know what 3 over 1 minus x even is. It doesn't think that way. It doesn't think to itself, hey, they just typed in 3 over 1 minus x. Okay, they don't think of it the way that humans do. Any kind of a computer calculator thinks of it as the equivalent power series centered at the appropriate location. So when it spits out a decimal, it's giving you a highly accurate power series, maybe 10, I'm just taking a guess because, again, that's not my area, but it could be 10 series. It might be 1,000 terms in the series that it's plugging that value of x into, centered at a nearby location to where you like. So computers know polynomials. They do not know rational functions. E to the x that I wrote a moment ago. Computer has no idea what e to the x is. It thinks of it as its power series. Same with natural log. Sine and cosine is really, really cool. And we're going to see the power series representations for all those things, not in this section, but in those last 2 sections. Pretty sweet. Okay, so something to look forward to. All right, so let's keep going. That was part A. Doesn't get any simpler than that. Let's do something a little bit harder. How about f of x equals 1 over 2x plus 5? Well, definitely a similarity, right? We've got a rational expression. Here's how this is going to play out, and it looks like I've got the final answer on the right side here. We want it to look like a over 1 minus r, okay? Now here's what's cool. A could be a constant. A could have a variable. It could have x in it. That's no problem. R is always going to have the variable x in it, okay? What we really, really need is that 1. That cannot change. We need that 1. So here's what we're going to do. We're really focused on the denominator. Okay, I've got the note right there. I need a over 1 minus r. Yes. So I'm going to begin just by switching the positions. Let's put the x in the second position, kind of just taking an easy step to get it ready. Once I have it written as 1 over 5 plus 2x, now the next goal, you see my note there out of the shadow, I need to make this a 1. If my x is here and I get this to be a 1, then I pretty much have it. A could be a constant or have x's. R is going to have x's, but that 1, that's got to be a 1. So what am I going to do to all 3 terms in my ratio here? I'm going to divide by 5. Everything gets divided by 5. Okay, and this is what happens. That's 1/5 That becomes the 1 plus 2/5 x. I kind of like writing it this way with the fraction and the x next to it. So 1/5 over 1 plus 2/5 x. Okay, something else that might be clear to some, but it's easy to miss. I need to have subtraction right there, right? 1 minus r. Well, no problem. I'm just going to think of this as, sorry for this shadow, woof, 1/5, and in the bottom, 1 minus negative 2/5 x. It's also written super tiny. Fractions within fractions tend to do that. 1 minus negative 2/5 x. Okay, now I can see the pieces. A, 1 minus r. Excellent. So now I can make the conversion back to my geometric series. A r to the n equals 0 to infinity. And that's what I've got right here. N equals 0 to infinity. My a is 1/5. My r to the n. If you're really curious, you could graph this original function and maybe the first several terms here, starting at 0. Compare those two. All right. Now the other part of the question was, what's the interval of convergence? Well, I always take my r, throw absolute values on it, say that it's less than 1. Okay. Negative 2/5 x, absolute value, less than 1. And if I just isolate my x, then I'll have it. The negative gets taken care of by the absolute value. Then I can multiply by the 5/2. Absolute value of x less than 5/2. So I know x must be between negative 5/2 and positive 5/2. But since it's a less than, it will not include the endpoints. There's the interval of convergence. So pay attention to that if you check out those graphs. Okay, sun's kind of peeking back behind the cloud. We're going to stop this video right here. We got a couple more, and they get more interesting the more that we do. I'll see you in part 2.